Welcome back, everyone. We're finally in week number 15. Here's where we're going to start wrapping up the course, getting everything finalized, going into finals week next week. And we're pretty much saying last on a lot of things. This is the last quiz. This will be the last unit we cover. And this will be the last document we go through to prepare for the final exam. Well, there's final exam information down below that I just couldn't quite scroll to get to. And I want to discuss the extra credit opportunities a little bit before we start as well. But any questions at the moment? Okay, well, pretty much Unit 8D is where the last content for the final exam is going to appear. And as far as the extra credit opportunities go, we mentioned there's an extra credit opportunity relative to the final exam, where if your final exam grade is higher than a minimum grade amongst these three grades, it can replace that minimum grade. So that way, if you had an off day, if there's one exam that wasn't your strongest, you can come back and make up that score through the final. The other extra credit opportunity is the course evaluation thing that you've probably had to click through on all of your courses. It's kind of like an annoying pop-up spam thing from what it's been described for me. The way this one works is the moment you're done completing your course evaluation for this class, just send me a quick message in Canvas or an email and say to let me know that you've completed the course evaluation, and I'll mark you down on my Excel sheet for the extra credit. It's going to be dropping the lowest two homework assignments in my lab, which some people are at 100% on the homework. That might not be the most exciting thing, but it means if you have just a couple sections where maybe you didn't get to that one problem or two problems, something along those lines, then you can wipe out those last sections. Finally, this one's not exactly an extra credit opportunity, but it is an opportunity to increase your score, so it's in the same grouping. I'm still accepting late work as late as Thursday, May 7. And that's 11:59 p.m. on Thursday, May 7. Anything that comes in before that, it gets graded, it gets included in your final course score. So any quiz that might have gone past due, any work in my lab that you want to revisit, you can come back to those. So those are the extra credit opportunities. I'll probably send some reminders about this one because it has a close date. I need to look up when that is, but I think it closes sometime on finals week. Again, I'll find out the exact time on that. But any questions at all with the extra credit opportunities or otherwise? Okay, last thing I want to talk about is just the final exam. The information got posted. I don't even know when. It was a kind of a busy weekend, probably around Saturday, maybe Sunday. This finally got completely updated. The final exam is going to be comprehensive, like we mentioned. For this exam, two 8.5 by 11-inch pages of notes are allowed, so ordinary letter size. And it's a good idea to start working on that now, say, trying to put these together as a frantic session, say Sunday night is a tough time to get everything you want on there. Take a look at what you put on your exams 1, 2, and 3, and look at the information that you really used on those exams to see how to potentially condense it now into 2 pages. A good idea is to go on a section by section basis. Notice the formulas that have been posted on the notes. For example, in the current section we're in, there's a grouping of 3 different formulas for the magnitude of earthquakes, for decibels, sound intensity, and we're going to look into the pH scale. So definitely include that kind of information. I'll be including on the last page of the real final exam this document, which isn't anything too major. It's going to be a set of unit conversions, as well as a couple major formulas for financing that we did in chapter 4. So this I feel like is kind of tedious to ask you to copy down. So this will be the last page. And these are the last 2 formulas as well. So everything else is going to be up to you to either memorize or include on your 2-page of notes. So that's the real page of the last exam, the final exam, just like we did on exams 1, 2, and 3. And now I have 3 versions of the sample exams. These are kind of long because, well, version 1 is the entire set of lecture notes from the first unit all the way to the last one we covered. Version 2 is slightly condensed. It's just another version of these same kind of problems, but this one says it's 57 pages. So probably the best way to use these sample exams is not necessarily to try to complete every single problem on that list, but it's more about targeting a section. If you feel like you have a section that maybe it wasn't your strongest that you want to come back to, maybe it was a statistics section, maybe it was, say, the loan payment section, anything along those lines, this is pretty much a huge packet of problems with solutions. For version 1 is in the Canvas because we solve these problems. So just scroll up to find that relevant section. For version 2, the solutions are at the very end of the document. Version 3 is now more condensed, but if you open this one, then it's not just deja vu. It'll kind of tell you what you're looking at right away. It's all 13 quizzes just put into one big packet. So it's a reminder that quizzes were very good problems as well. You should know how to do all the quiz problems. So if you're familiar with all of these, you'll be in great shape. As well as take a look into your exams 1, 2, and 3. If you revisit those, that will tell you pretty much everything that can be on the exam, except for the problems that were in Unit 8. So version 2 is going to give you a nice roundup of Unit 8 problems. And for this document, this is the one that we're going to be reviewing when we come back on Wednesday's class and Thursday's class. Here's where I attempted to do the impossible, take about 15 weeks of work and condense it down to something more reasonable. So this is the more way cut down sample final exam that we're going to go through on a problem by problem basis. This one is 7 pages long. So probably a little bit longer than a real final exam, maybe about the same length. It seems like it's loading in kind of slow. But we'll take a look at this in much more detail as we go through. Hang on, I think I uploaded the wrong file on that. Uh-oh. That was a final exam review. Let me see what I have going on here. Hang on, I think I got one of my classes mixed up. I might have the right file here. Let's take a look at this one. Definitely have the file here. So I'll get this converted and shared if I don't have the correct one on this set of notes. Okay, here's the real exam. Sorry about that. I got my statistics class mixed up with this class. That's not good. Again, it was kind of a busy weekend, so things happened there. Probably should fix this right away. So this is not the real one. We'll go over this one right here. Okay, you can find the correct document in the blank lecture notes. And let me throw in the correct document here as well for easier reference. Okay, that's our real review there, finally. Well, that's what we have going on so far for the week. We're going to finish off Unit 8D. If we have some time today, we're going to start this review, and we'll definitely be spending the rest of the class time, Wednesday and Thursday, looking at these problems. Trini says, do you have a general idea how many questions will be on the final? I think it's going to be around 12 or 13. So I don't know the exact number. I wrote it, but I forgot. But it's going to be definitely not too long. It's going to be a pretty nice roundup of all the units that we've covered in this course. And just because Chapter 8 wasn't on any exam, doesn't mean I'm going to load it up with a whole bunch of Chapter 8 problems. So I'm probably only going to put it down maybe around 2 problems from Chapter 8. So maybe something from, say, we mentioned Unit 8C is an extra credit question. So there's a real extra credit question using the logistic growth model for Unit 8C. So more along the lines of a single problem for Unit 8.8B, half-life or doubling time, and one problem from Unit 8D. Thanks for asking about that. Other questions at the moment? Okay, well, let's start off our unit or finish off our Unit 8D. We're pretty much most of the way through it. I think there's 4 more problems to take a look into. Let me expand this out. Here were the problems that we solved going into the weekend last Thursday. And just as a kind of refresher on what we did on these problems, we were using these ideas. So we're looking into the intensity of sound measured in decibels. And it's a pretty tricky table because all the information here is indexed against the softest audible sound. It's a relative scale. So this is what we're thinking of as the baseline in terms of loudness with decibels. Interestingly, it goes to negative for inaudible sounds. So if we look into the softest audible sound and take any row that you see on this table, say 100 decibels, that's going to be a siren at 30 meters away from us, the loudness. But look at the way it's defined. It's saying it's going to be 10 to the power of 10, but that number has no meaning unless we read the column. It's 10 to the power of 10 times as loud as the softest audible sound. So somewhere down here, every value here, its intensity is just how many times louder it is than that softest audible sound. So when we looked into example 4, it was asking us what is the loudness in decibels of a sound 1,000 times as intense as the background noise in an average home. We went to the background noise of an average home, 10 to the power 4, 1,000 times as loud as the softest audible sound. So we put in the 1,000 because it was 1,000 times as loud as the background noise in a home. Here's the 10 power 4 coming from here with the orange box. But that's 10 power 4 times I naught, where I naught is the intensity of the softest audible sound. So I naught is just part of these formulas. It's just part of life. But they're strange because in the problems that we're asking in these notes, they always cancel. For the example 4 problem, we use this formula directly. We threw in the intensity in the numerator, put I naught, the softest audible sound intensity, in the denominator. Then we worked out the logarithms, got 70 decibels. Well, 70 decibels is 1,000 times as loud as the background noise in an average home. And they wouldn't have never guessed that. That's kind of interesting. But any questions with that recap problem there? Okay, well, there's really 2 sets of formulas. We're going to review a problem just like example 5 with a different context. The other set of formulas is this one. If we're comparing sound intensities, and we're not computing the decibels, but we know the decibels of some sound that's occurred, then we can look into the intensity of that relative to the softest audible sound by taking 10 to the power of the decibels, divide by 10. So whatever that works out as a total exponent, we put on a power of 10, and that's how intense that sound is relative to the softest audible sound. And because the softest audible sound just keeps on coming up over and over again, we called it I naught. We readjusted the formula by clearing out the denominator, and we can say the intensity of a sound is this part right here times I naught once again. So that's what we did here on example 5. We used the formula twice on this one. Let me highlight that formula a little bit better. Okay, here's the formula once again. So we were just asking a generic question, no context. How much louder is 95 decibels as a sound than a 90 decibel sound? We interpret this as how many times louder, or how many times as intense. We found is 3.16 as intense, just going up by 5 decibels, 3 times the sound intensity and a bit more. And the way we did this was we just used the intensity of a 95 decibels. That's a part in blue. We plugged in 95 in green, divided by 10. That formed the numerator, and we did the same exact operation. We worked the formula twice for the denominator. So we're going to do that again in example 6, but we're going to split this up. Let's consider the formula just as a one whole problem for the numerator, one whole problem for the denominator, and then we'll put them together to answer the question. So that's our recap. Now we're about to jump into example 6. But any questions at all before we get started? Okay, we briefly took a look at this one before we ended and went to the weekend on Thursday. So this one is a really crazy bit of history that's occurred. The loudest sound ever measured in human history was the catastrophic volcanic eruption of the Krakatoa volcano, I'm assuming, in Indonesia. It occurred on 1883, August 27th, and people on the island of Rodrigues in the Indian Ocean, which was about 3,000 miles away from this eruption, report hearing what sounded like a distant roar of heavy guns. And that's incredible being 3,000 miles away. A way to put this in context for us is we're told that this is roughly equivalent to a sound occurring in New York being heard clearly in San Francisco. So this was shocking and it caused humongous amount of damage. Here's a real historical context. This is something that has been recorded. The captain of the British ship, Norham Castle, which was 40 miles away from the volcano, noted in his log, the explosions are so terrific that the eardrums of over half my crew have been shattered. So there's lots of accounts of this. The sounds pass across the globe. The sound passage across the globe was recorded by barographs of multiple places on the planet, which are record atmospheric pressure. And another crazy bit of trivia is that the pressure wave created by this circled the Earth 3 to 4 times in each direction. It took about 5 days to dissipate, no longer being measured by the barographs. So when they try to extrapolate how loud was this in terms of decibels, this is the figure that they come up with, 310 decibels. And we have to be honest when we state a figure like that the decibel system that we're looking at, the scale, the physics of sound waves itself, it actually caps out, I believe, around 190. I think more precisely around 192. Beyond that, it becomes a sonic boom. It's a shock wave at that point. But if they were to extrapolate and think in terms of energy, just intensity, this is the number that they come up with. 310 decibels would be the loudness if a sonic boom didn't actually occur. So in terms of that, 310 decibels, using the decibel scale, we're going to answer the question, how much louder was the eruption of Krakatoa than the sound of a jet 30 meters away? For an exam problem like this one, I would have to cite the table, a jet 30 meters away, is 10 to the power 14 times as loud as the softest audible sound. So that information would have to be included. But now we're essentially doing a problem like example 5 in a slightly different style. We want to find the intensities of the two events independently. Any questions before we begin? Okay, well, here's our formula, I've screenshotted in to help us out. So we can say now the intensity of, let's start with maybe the Krakatoa eruption. It's what comes first, and typically when we make a comparison, we want to consider the item that comes first when we're comparing. So intensity of Krakatoa this is going to be equal to, we take 10 to the power, and as one whole exponent, we're going to take the loudness in decibels, which was 310 decibels for the Krakatoa eruption. That color coding might get confusing. Let me reset it this way. So take 310, divide it by 10, and it gets multiplied against I naught. So this is telling us how many times louder was this eruption at Krakatoa than the softest audible sound. So that's 10 to the power 31 times as loud as the softest audible sound. So that's where I naught goes in for this computation. And there's no simplifying beyond this point. It just stays at that stage. And now we go over to the other event, a jet 30 meters away rather. Which means we just run it through the formula a second time. We're going to have to cite that table with the sound scales. Let's write in to organize intensity of a jet 30 meters away Same exact organization, but different decibels. This is going to be 10 to the power of. Then let's cite that table. I've already forgotten. That one is, in terms of decibels, 140 decibels altogether. So take 140, divide that by 10. Let me fix the bracket first. Multiply by I naught. This division goes nicely. This is just 10 to the power 14 now. Times I naught. So we have two values. We want to know how much louder was the eruption of Krakatoa than the sound of a jet 30 meters away. Essentially, all we're going to do now is just make a comparison by dividing the two. Well, we're done with the formula. Any questions with the formula used so far? Okay, and since we're kind of in review mode, it might not be a bad idea to pull up this problem. It's been a while ago, but it's kind of gives us an idea of how the logic goes when we compare these kind of events, whether it's earthquakes or loud sounds, like in this case. I think this is a problem that we looked in Unit 2B. We were doing some early work on units. We're comparing things along the lines of gigawatts to megawatts, and this was asking how many times as large is a gigawatt. A gigawatt is how many times as large as a megawatt, is the way it was actually written. All we did was we took the thing, whatever it was that came first, it forms a numerator. Take the other quantity, forms the denominator. Divide the two, however the math falls. It doesn't necessarily have to be the biggest thing on the numerator, but it typically is. And after doing the work, canceling the units, working with the powers of 10, we found that a gigawatt is 10 to the power 3 times as large as a megawatt. In a real sense, that's all we're doing here. We're just now comparing intensities of sound. Krakatoa came first, so that's going to be our numerator, much like the gigawatt, and the jet will be the denominator. So putting this all together, here's what we're going to get. Our computation goes 10 to the power 31 times I naught, being divided by 10 to the power 14 times I naught. So the softest audible sound that we've been tracking very carefully. Again, it's weird because it's a critical part of the formula for what the formula is even trying to say. But in our computations, they cancel out for the problems being asked in my lab. So for the same kind of problem that could potentially be asked on the final exam, it's just gone after cancellation. So this just becomes 10 to the power 31 minus 14. So we're doing the same essential thing that we did back here. We're using, let's see if we wrote that down. Yeah, here's our scratch work. We're using exponential laws that says if you bring the base 10 into one spot in the numerator, oh, we did it a different way. Looks like we did cancellation there. But if we use this formula that we cited but apparently didn't use directly on paper, all we're doing is taking the exponent in the numerator, subtract the exponent in the denominator. So that's why this is 10 power 3, 9 minus 6. I guess down below is just a comment to say you could also do it that way if you prefer. So 31 minus 14 would give us 10 to the power of 17 altogether. And that's our work. Our work is done at this stage. We can say put a final finishing touch on it by saying the eruption of Krakatoa was 10 to the power 17. That is a very, very high order of magnitude times as loud as a jet 30 meters away. So that was a really, really insane event. Well, any last thoughts or comments, folks? Finishing off the decibels part of the notes. Okay, well, we have just one last segment to get through. Now, this is the segment where we're going from not just scales, say like magnitudes of earthquakes or decibel intensity of sound. We're now doing something with chemistry, which means the definitions start to get a little bit more interesting. But the formulas, they're not too bad. It's just a new set of formulas. So my advice for the final exam, I'm going to ask one question maximum from these notes. So if you have all three sets of formulas down, they're fast or right, you'll be in good shape. If a scale like this is needed, or if a scale like this one is needed to answer the question, I'll just write in the information in the problem so that you don't have to look up a table like we are in some of these problems. Okay, so here's the so-called pH scale. It's defined by the following equivalent formulas, and these are pretty interesting formulas. pH is either defined to be negative times log base 10 of H plus with a bracket, which means in chemistry terms, concentration typically, or bracket to meaning again, concentration of H plus equals 10 to the power of negative pH. So these are strange formulas that we need to take a kind of a close look at before we get started to see just what's going on. But the short of it is pure water is considered to be neutral on the pH scale. If we have, with a pH of 7, so here's pure water, our neutral. Acids have pHs lower than 7. So anything around pH of 2 is highly acidic. Something around 1 would be very, very acidic, and so on. Bases, by bases we mean anything along the lines of, say, baking soda or some of the scary stuff like ammonia, drain opener, lye, anything along those lines, have high pH. So that's the scale so far. There's a lot going on. So I want to kind of explain what is H plus. What do we mean by concentration and moles per liter of a hydrogen ion? There's a lot of moving parts here. All I did was copy the formula verbatim, but then when I tried to practice a problem, I realized my chemistry training needed a little brushing up, so I did some research on this. But any questions or comments so far, folks, on just the definition of the formulas or the scale? Okay, well, let's relate this slightly to what we've done before. If we have problems like these, whether it's loudness or intensity of a sound, or going back even further, it's energy released in an earthquake or the magnitude of the earthquake, the idea is the pH is kind of like the magnitude or the decibels. So we're going to track that quantity there in these two locations. And whenever we say energy released from an earthquake or the intensity of a sound, however many times more intense it is than the softest audible sound, here the analogous thing is going to be the H plus. So all these formulas can essentially be color-coded in the same kind of way, which kind of helps organize how the quantities are going to be used. The scale is for pH, so that's the thing that's in green, just like on the other formulas. Now, the next thing is, we should say what we mean exactly when we say hydrogen ion concentration. In other words, the whole thing just becomes a mystery computation if we don't know exactly what we're thinking about when we say that. So when you say H plus, we're talking about an ion of hydrogen. And if you're like me and you haven't taken a lot of chemistry, that's okay. But think in terms of atoms with a really basic model of having a proton, a neutron, and an electron, except hydrogen atoms are some of the basic, most atoms. They typically just have a center core, a proton, and an electron. But if you say hydrogen ion, H plus, this means this is a hydrogen atom with no electron. And that's what the plus is saying. It has a positive net charge because it lost its electron. So all that really is, that whole symbol is just a proton. It is a proton. So that's a okay way to designate what we mean by H plus. Just think of an atom without an electron, a simple proton itself. And if you write this, in chemistry, a bracket, like we mentioned earlier, typically denotes a concentration. So this is now, in terms of what we wrote above, concentration of protons. There's a whole lot more to the story. So to see more, to make this more precise, you need to take a chemistry class, probably a couple of them. Physics wouldn't hurt either. But this is a good way to explain it just to start off. What is going on with the pH scale? So H plus is hydrogen ion concentration, just the number of protons in moles per liter. And that's where, again, I've heard the word before, but if I didn't research this before class and someone asked about it, I would say I have no idea. But anyone happen to know what a mole is? Not the animal. Again, it's one of those really weird quantities that makes these whole problems just feel kind of weird and mysterious, because if you throw this information at us and the textbook doesn't really define it at all, then it feels like everything we were doing is a mystery computation. It went into a black box, we got a number, but we have no idea what we've even computed, making these problems strange, very, very strange. So when I looked up what a mole is, just to get really precise, a great analogy came up. It's like using words dozen. If we say we have a dozen eggs, it's just saying we have 12 eggs. Now, if we say we have a mole, 1 mole, it means this. 1 mole is, here's this particular number, 6.02214 times 10 to the power 23. This is sometimes called Avogadro's number over I believe, a German chemist who came up with the idea mole, which is short for molecule in German. So 1 mole is this many molecules. It's a gigantic number because we're thinking of a different kind of scale rather than eggs, dozens fine for a number. If we're talking about, say, protons, these things are very, very tiny. And so we need a gigantic number to describe a cluster of protons. So that's what a 1 mole is. And I have a nice comparison to kind of get our mind around that number, to get a feel for what that is saying. So here's the next part. I need to copy this down to get this just right. So 1 mole of water is 6.02214 times 10 to the power 23 molecules of H2O, the chemical compound for water, and weighs about 18 grams and is roughly a teaspoon of water. Okay, so that's what's going on with this whole sentence right here. A lot of stuff. So think of H plus, number of protons, and we are using, when we say a number of protons, this number particularly per liter of whatever you're considering, per liter of lemon juice, per liter of coffee, per liter of maybe household ammonia. The pH scale is just saying how many protons are there in terms of Avogadro's number, 6.022 times 10 to the power 23, or just say moles for short, in all these different kinds of liquids. So that pH scale will give us a sense of acidity and base. I guess that's basicity is probably a good way to say that. So that's what a mole is. Any questions or comments so far before we try out a few problems? Okay, unlike the prior problems, everyone has a good idea what magnitude of earthquake is representing, or sound intensity in decibels, but this is the one that's really hard to really nail down. What exactly are we doing? So that's finally definition, explains what the H plus is in both of these formulas. And here's some typical problems that come up in the MyLab homework. Something along the lines of, we're told the pH of black coffee is about 4.9. Depending on the coffee, I mean, some coffees are more acidic, some are less, but let's assume that on average, we have coffee being brewed at that pH at some diner. We want to know what is the hydrogen ion concentration, which sounds like the most abstract statement ever, right? And it really is abstract. But if you're being asked what the hydrogen ion concentration is, just means you use this formula where the red dot is, which is great because we have a number for pH. We can plug that in, answer this question immediately. So as abstract as this whole set of formulas are to define, as abstract as the equation is to say, this is all we're doing. When we say hydrogen ion concentration, we're going to write out H plus, just to remind us what formula we're using, is going to be 10 to the negative of pH. So let's drop in our values. We have 10 to the power of negative 4.9. So that's our value. It's not done yet, but we're nearly there. We're done with the formula right at that step. Any questions or comments at the moment? Okay, when you do a problem like this, it feels like it's done. I think this came up before in just this unit. I made a loose comment that said, but that's not in scientific notation, and it's true. There's an exception here. Scientific notation means you have an integer, not a decimal number, not a fractional number. You have something like -5, +7. -4.9 right here causes a major problem, which is really easy to miss, can make the homework confusing in this section. So this is not in scientific notation. Reason being, it's not a whole number. That's okay. It just means we need to throw it into a calculator, get a value out. So now, citing Desmos, we want scientific notation with 2 significant digits. So just throw in 10 to the power -4.9, and it's 1, 2, 3, 4 zeros. 2 significant digits will start at the 1, go to the 2, but it'll round up to a 3. So H plus after we throw that into the calculator, 0.12341 is the result of 10 to the power -4.9. Now we can bring that back to scientific notation. We need to scoot the decimal point 1, 2, 3, 4, 5 values to the right. So this becomes a 1.3 times 10 to the power. If we go right by 5, we need to put in a -5 because that's what will make this quantity here smaller. So that's all we had to say. That's the hydrogen ion concentration for black coffee when it has a pH of 4.9. So that's one computation down. I want to say a couple more words about this to just explain what did we even compute? What does that mean? But any questions at all? Just getting the number? Okay, well, relating to everything we've said about hydrogen ion concentration, H plus just being a proton, what a mole is, we can say that this is, in terms of, let's maybe write a new sentence, I think that'll flow better. We can say that the hydrogen ion concentration of black coffee is 1.3 times 10 to the power -5. Recall hydrogen ion concentration is moles. Moles of hydrogen ions, which are just protons from our discussion over here. That's all H plus is. It's just a proton. So it's 10 to the power negative 5 moles of protons per liter of, so that's the per liter right here portion, and it's per liter of the black coffee, whatever solution that you would usually say in chemistry we were considering. So the answer is this, and this is just a comment down below to kind of make sense of what did we even calculate. And we can go just a step further if we wanted to. If it's 1.35 times 1.3 times 10 power negative 5 moles of protons per liter of black coffee, you can do the following computation. Not required in the homework at all, but this kind of helps to show just what did we really calculate. 1 mole is that number molecules. So if we take that number, Avogadro's number, 6.02214 times 10 to the power 23, multiply it against the hydrogen ion concentration, the number of moles of protons per liter black coffee, we take 1.3 times 10 power negative 5, we get to that number. And what that number is telling us is the number of protons that are completely bare, no electrons around them that would make them a hydrogen atom. That's the number of protons that is going to be in 1 liter of black coffee. This is what's swimming around in your drink. So kind of an interesting side thought. So you can always take this, take the unit moles, swap in the number, multiply. And it just tells you how many protons is in whatever substance you're looking at. We typically just end like this. You can put units on if you like, but this would be a completely acceptable way to end your answer. Okay, the pH is a kind of an odd scale. It's interesting to think about. It's a pretty good refresher or introduction to chemistry. Any questions or comments whatsoever with the conclusion here? Okay, well, our goal is just to practice a couple more questions along these lines. So we used example 7 with minimal context just to give us a sense of what the formulas are saying in the very first place. And really, just like decibels, there's 2 formulas we're using. Either the one on the left, if we have to compute pH, we need to know the hydrogen ion concentration. Or if we know the hydrogen ion concentration, we can find, hang on, I said that backwards. If we know the pH, we can find the hydrogen ion concentration like we did on example 7 with the known pH of black coffee. So now, if we turn this all around, this is a problem that's kind of similar, a comparison problem. We want to know how much more acidic, or how many times more acidic, we could say differently, is pure water than baking soda. This is one of those problems as a final exam question. I would have to tell you the pH of both. From a problem like this one in, say, my lab, it's assumed that you're going to look up this scale for pH. They'll provide a scale as a link usually in the problem. So let's grab the scale to help along with the problem. So we want to know how much more acidic is pure water than baking soda. So let's grab our quantities. Pure water has a pH of 7. And then next quantity we're taking a look into is baking soda. So another peek at the table. Baking soda is at the basic end. Pure water is neutral at 7. So this is at pH of 8.4. A question asks, how much more acidic is pure water than baking soda? Which is kind of a strange question to ask. What we're not doing is dividing 7 by 8.4. And if you think back to what we did in prior problems, we didn't do that when it came to earthquakes either. If we were asking how much more destructive or how much more energy is released in, say, a magnitude 8 earthquake versus a magnitude 8.5, what we had to do is write out the energy released. So say in this comparison here, we had to find the energy released for the 2004 quake, energy released for the 2011 quake, and then divide those results. For this problem, because it's pH, the thing that we're going to do this time is find the hydrogen ion concentration, much like we did for analogously the energy here, and then divide the hydrogen ion concentrations. Another way to know that that's on the right track is that if they gave you a pH, plugging it here gets us nowhere, but we have something to work with. If we plug the pH there, we can find the H plus. So this is a tricky question, especially with the wording. When it's asking how much more acidic, we're talking in terms of H plus specifically. Much like, once again, analogies are always pretty helpful. We were asking how many times more energy was released in one quake or another. We were saying in terms of the magnitude, but also the energy released at the same time. So now we can do the following. Let's say for pure water, I have a feeling this should probably go on the next page. Let's drop this down below. For pure water, we can say H plus concentration, number of protons per liter in terms of moles of protons, is going to be equal to 10 to the power of negative its pH, so -7. Then do the same thing with the next quantity for baking soda. The hydrogen proton ion concentration is going to be 10 to the power of negative, never forget the negative sign, put in the pH, 8.4. So we just put those figures together. We want to know how much more acidic is pure water than baking soda. And so again, it's much like doing this problem. Here we're asking how many times as large is a gigawatt than a megawatt. Really, it's the same question, except we couldn't ask this question in Unit 2B because we didn't have these formulas yet. We hadn't even defined logarithms at this point. But same idea, pure water came first. We're going to put pure water in the numerator in terms of the hydrogen ion concentration, H plus. Baking soda is going to go in the denominator. So that's our next computation. Write out 10 power -7 divide by 10 power -8.4. And you could throw this into a calculator to get down to 2 decimal places if you like. If you want, you can use properties of exponents to rewrite this as 10 power -7 times 10 to the power. This in the denominator we can bring up now into the numerator, force the exponent positive. So now it's 8.4. In this configuration, the exponents would add together. That means it'd be an 8.4 minus 7, or a 10 to the power of 1.4, and that's what we're throwing into our calculator. To 2 decimal places, 10 power of 1.4 is 25.12. Again, you didn't necessarily have to do this step. If this was something that comes up on the exam, maybe a different problem, but same kind of exponent work, I'm never going to take off points if you did something like this, 10 power -7, divide by 10 power -8.4. Really, the only danger is you have to be very careful when you put in those negative exponents to make sure everything comes in the exact same way so that we don't have any error inside the calculator. So doing it this way on paper sometimes is a great protection because sometimes the calculator import can be trickier than the arithmetic down here. So now if we have a 25.12, we can say pure water. The thing that came first here is 25.12 times as acidic as the second quantity with that pH 8.4 as baking soda. It's quite a lot. We went up by 1.4 from pure water to baking soda in terms of the pH scale. That was a difference of almost 25 times more acidity, more hydrogen ion concentration going on. Well, in some sense, you probably aren't too surprised because we saw the same thing with, say, earthquakes going up one order of magnitude with earthquakes. Magnitude 7 to magnitude 8 represents about 32 times more energy for magnitude 8 than magnitude 7. Well, any last questions or thoughts at all, folks? Finalizing this example here. Okay, well, this will be the last question for the notes then. Let's turn this over to a problem now that has a little bit more context, but nothing too crazy going on with this one. Let's throw this down below for reference for when we need it. So now this one is about the lithium hydroxide. So this is one of those chemicals that seems to be vital for just our modern existence in year 2026. It has sensible applications such as carbon dioxide scrubbers. It's used in sealed environments like International Space Station, military submarines. I believe this was used for the Apollo mission to the moon. So it's a very important chemical. Lately, it's a precursor chemical used in the production of cathode materials for modern lithium ion batteries. That's in just about everything: smartphones, wireless headphones, electric cars, and so on. So finding lithium hydroxide, mining this stuff, has become some of the biggest business of all time in 2026. And we're told next, a chemical manufacturer produces a solution of LiOH, lithium hydroxide again, with a hydrogen ion concentration of that figure in terms of moles per liter. So when you see hydrogen ion concentration, think this is referring to H plus. If I can get that plus symbol in there correctly, let me try again. Moles per liter is another giveaway per our definitions. What we're solving this time is, what is the pH of lithium hydroxide? Well, this one's a little bit different, right? We used this equation to the right in two examples already. But this time, what we're trying to solve for is the pH itself. That means the dead giveaway of what to do with that number is it's got to go inside there in order for us to get the pH. So we're going to use that number to compute pH of lithium hydroxide. Okay, I think I'm back. Sorry about that, folks. Zoom is really, really angry today. I'm not too sure why. I don't know if this is a bad internet connection going on or something along these lines. But I'm going to take a note of this and see if I can get some technical support on this. We just have two more classes to go through, but it would be a painful review if it kept cutting out over and over again like this. But sorry about that. Just to double check, can you all still hear me at the moment? Okay, thanks, Zach, for the heads up on that. That's got to look weird from your side. From my side, it just says Zoom disconnected, trying to connect, and then everything just suddenly pops back up. I'm assuming the recording's still going, so maybe it just doesn't like this problem. Let's see if we can get through this problem without offending the Zoom overlord. So we're trying to find the pH of lithium hydroxide. All we're doing now is taking this figure, the hydrogen ion concentration, and dropping it into the formula. So this is going to be negative log of 1.0 times 10 to the power negative 14. So this is all we have to compute next. Echo says this problem is cursed. We should definitely leave it off the final. Probably not the worst idea. Now that we're nearly done with these problems, I'll give one hint on the final. A good set of sample exams on any final, any exam we were going through, a good set of sample exam problems was always the quizzes. If you look at what's going on in the final quizzes, it was magnitudes and earthquakes, meaning that's probably a good hint on what to be ready for. But we're solving this last one just to prepare for the homework, the last unit for the total semester. Now all we have to do is throw that into a calculator. But if you've had a lot of practice with logarithms, this one's really, really fast. Let's throw it in just to show what it would look like. And then recap on what logarithms to base 10, forgot my base here, really does. Let me throw in that 10. So if you put this into the calculator really, really carefully, it would go negative log. This is to base 10 in Desmos. We can leave off the 1 times. 1 times the number is that number. Throw in 10 to the power negative 14. And it becomes just 14 itself. So that's the exact pH. But what's really happening is there's a cancellation that goes through like this. A base 10 logarithm cancels all the way through the 10. It just becomes a negative 14 times the negative 1. So either way you'd like to visualize this comes out to a pH of 14 altogether. This one's off our scales, but we can still answer the follow-up question next. First, any questions whatsoever, just coming up with the pH? Okay, well, back to our scale. Somewhere down here. Here we go. Here's our scale. And again, we're off the charts on this one. This is a real chemical. The hydrogen ion concentration is realistic. So what would you all call this thing? Is lithium hydroxide an acid or a base? Based upon the pH of 14. Yeah, absolutely, Amy. This one is a wildly, extremely strong base. One of those things where, some chemicals in this range that if you even touch it, it can cause damage. Lye drain openers, if you were to swallow any of that, that could be fatal. This is many, many, many times worse. So this is one of the more dangerous chemicals. This is a major base. Well, we did it, folks. That's the last complete question that we have on the unit. These set of problems are like we did for all the other units. They're pretty parallel to what you're going to be doing in the homework. If you come up upon any that are tricky, don't hesitate to ask about them, whether email office hours, say during the review, I'd be very happy to help out. But again, pH is kind of a weird scale. It's hard to even define what's going on when you say things like hydrogen ion concentration. So that makes it a good unit to end on for the course. For now, we're now fully on review mode for the rest of our time this week. So let's close out these. We're going to be spending the rest of our time going through the final exam review. And as far as the final exam goes, again, it's not going to be too long. I can't ask every single one of the questions, even from every one of these versions. So my job is to try to find a representative sample amongst all of the chapters. Pretty much what I did was I went from a chapter by chapter basis and picked around 2 to 3 problems, usually closer to an average of 2 per chapter. I think it landed around 12 to 13 questions. There is an extra credit question in the real population growth using the logistic growth rate, because I felt like that one was kind of getting a little bit out of hand when we were doing it on the notes. So there will be an extra credit purely for extra credit. And after writing the exam, I wrote this to be our review for us for this week. But if you do have problems that you would like to take a look at, let's get this table going. If you have problems other than what's on here that you would like to take a look at, don't hesitate to ask about them at any point, even today or any point during the review on Wednesday and Thursday. I would love to prioritize your questions, even over the questions on this document. And whatever problems I might not solve on the end on Thursday, I'm still going to go back to these after finishing grading on Friday, get them fully solved. This will be posted right where it sits here if you want to refer back to it. Okay, well, I think we have time for one problem. How about we make this problem number 1 our last problem of the day? It says the width of the European Union is approximately 4,000 kilometers. Convert this figure into feet. And that means we're just using some unit analysis, doing a conversion. If this is a problem that comes up on the final exam, first thing I would do is go to the very back formula sheet. So this is on the last page. And we have something given in terms of kilometers. Kilometers relates to miles, but we want something in feet. Meters relate to feet, metric to United States customary system. And we have kilometers, so we need the prefix table as well. So let's just grab everything here and use this as we go. Okay, so with that table there, just imagine we're just eyeballing this last page on the exam as we go to solve. If the European Union is 4,000 kilometers, and we want to convert that to feet, first thing we can do is take, say, the kilo prefix for K, that's just meaning 10 to the power 3 or 1,000 meters. So if that's the case, coming back here, we have 1 meter is 3.28 feet. But the trouble, though, is this is in meters. We want to get it into kilometers. But this table helps us out. If we multiply both sides of this equation by 1,000, the unit can be converted into a kilometer on the left, and just multiply the right-hand side by 1,000 as well. So take 1,000 times 1 meter, take 1,000 times 3.28 feet. On the left, we have 1,000 meters. On the right, multiply this by 1,000. We have moved the decimal 4 spots to the left, to the right rather, 3,280 feet. But now this can be converted into 1 kilometer is now 3,280 feet, which is great because we're converting into feet. The first thing we had to do is really just come up with our conversion factor. So here's where the 2 parts of the table we had to use to make that happen. So once we get that block of information down, Now we're just going to run through the unit analysis on the 4,000 kilometers. Any questions on the moment with making these jumps from here all the way down to the kilometer conversion? Okay, now putting this all together, take 4,000 kilometers. Multiply this. Everything on my taskbar just disappeared. Hopefully Zoom is still stable. Multiply this. Maybe what I should do before class next time is just restart the computer. That might be a helpful thing to do. Take this 4,000 here, multiply it by, we want the kilometers to cancel out, so we should put 1 kilometer in the denominator. 3,280 feet into the numerator. This causes kilometers to cancel out, and now we just have a unit that's in nothing but feet. So back to this calculator. Take 4,000 times 3,280, and we get a large figure. It didn't say anything about significant digits or scientific notation or even rounding. So however you decide to format the answer is up to you. But it looks like it's 13,120,000 feet. So that's the width of the European Union from the westmost point somewhere in Portugal, I'm assuming, to the eastmost point. Not very good at geography, but somewhere around Poland, I'm assuming. That's the width in terms of feet. We'll try out a bunch more problems on Wednesday, but I think this is a pretty good stopping point for us while the computer tries to figure out life and Zoom stops being angry. But any last questions at all before we call it a night? Okay, once again, when we come back on Wednesday, I'm pretty much just going to go in the order of the problems you see here. If there's a problem down on the list you want to see done first, or any other problems that you'd like to see done that are your suggestion, don't hesitate to interject at any point. So this is pretty much my review in lieu of questions. But have a great night, folks. I'll try to talk to the tech people to see what's going on with this computer or the Zoom install, and hopefully have a better, more stable session. I'll try to remember to restart the computer as well. But take care. I'll see you all Wednesday.